Let's take a look at the next example in section 4.4. We're asked to solve y double prime minus y prime plus y equals to 2 sine of 3x. Again, this is a linear differential equation with constant coefficients. We have y double prime, coefficient of 1, y prime has a coefficient of negative 1, y has a coefficient of 1, so it's linear, constant coefficients. So we can solve it with the method we just talked about a moment ago. Step 1 is we're going to find the complementary solution yc by solving the homogeneous differential equation y double prime minus y prime plus y equals to 0. In order to do that, let's go ahead and solve the auxiliary equation. We have m squared minus m plus 1 equals to 0. Let's go ahead and solve this. It won't factor. A is 1, B is negative 1, and C is positive 1. So we get that m equals the negative of b, that's going to be the negative of negative 1, which is positive 1, plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So we get m equals 1 plus or minus the square root of, it's going to be a negative 3 on the inside, divided by 2. And so we get m equals 1 plus or minus I radical 3 over 2, which is equal to 1/2 plus or minus I radical 3 over 2. Okay. So if we recall, this is something we saw back in section 4.3. Whenever we have complex conjugate solutions, okay, then essentially what's going to happen is the solution should be of this type. It's going to be y sub c equals, we have c1 e to the alpha x times, actually let's factor, I guess we can factor it out. So we have e to the real part of the complex number, we call that alpha x, times c1, the cosine of beta x, where beta is the imaginary part of the complex number, plus c2 times the sine of beta x. So our complementary solution in this case is going to be y equals alpha is 1/2, beta is the radical 3 over 2. So we have e to the 1/2 x times c1 times the cosine of the square root of 3 over 2x plus c2 times the sine of the square root of 3 over 2x. And this would be our complementary solution. And I'm going to write this up in the right-hand corner because we'll come back to this later. Just because we're going to need a little bit of space for what comes next. We now need to solve the particular solution. And I'm just going to use a shorthand. So many of you might not know this. Hopefully I can get rid of this thing. Go away, ruler. Let's see. Undo my delete. Okay. I miss the old days when we had tons and tons of whiteboards. So I'm just going to use a shorthand notation here. Just to remind myself, so I'm going to erase quite a bit here. E to the 1/2 x. And I'm just going to say CIS. Cosine I sine. It's not really technically correct, but it's close enough to remind me at the end when we need it what YC was. Now the important part is now we need to solve for the particular solution, okay? And this is when we look at the non-homogeneous differential equation. So now we're going to consider the right-hand side. That function, the textbook, in the notes, we call it g of x. G of x is the following here. Okay, so g of x, it's a constant, it's essentially just a trigonometric function. It's the sine of 3x. If we think about how the derivative of this function would go, the derivative of sine is cosine, derivative of cosine is sine. So it's important to consider that in this part here, if we're trying to solve for y particular, even though you only see a sine on the right-hand side, we're going to make the following assumption for y particular. So let's assume that y particular is going to be equal to, let's call it a times the sine of 3x. I guess technically we usually put cosine first when we write these out, but I'll just go ahead and do that. Just to stick with conventions. We'll say a cosine 3x plus b sine 3x. And the reason why we're including the cosine is if I look at this term in the differential equation, we know that the derivative of sine is cosine. So it's very likely that a cosine term may make its way into our particular solution, and in general this will always be the case. If your g of x is of the form of constant times either sine or cosine, always include both that function and the other one along with it. Okay. In a little while, I'll actually kind of highlight, and there's a fantastic list that's in the textbook that will kind of give you suggestions as to what to try for your y sub p when we're doing our method of undetermined coefficients. But again, right now, it should hopefully make sense to you all, and it's at least believable based upon the kind of things we've seen, from past calculus courses. So let's assume that this is going to be our particular solution, and our goal is to solve for those undetermined coefficients a and b, such that y sub p will be a solution to this differential equation. In order to plug this into the differential equation, we need both y prime and y double prime. So y prime, according to the chain rule here, be very careful, but you're going to end up with the derivative of the first term will be a negative 3a sine 3x. The derivative of this term would be a 3 cosine, I forgot my b, 3b cosine 3x. And now we need the second derivative, so y p double prime, that's going to be equal to negative 9a. That would be the cosine of 3x. And now this will be negative 9b, the sine of 3x. So we have y prime, so we have yp, y sub p prime, and y sub p double prime. Let's go ahead and plug them into the differential equation. So it's y double prime. Y double prime is negative 9a cosine of 3x minus 9b sine of 3x minus y prime, which is negative 3a sine 3x plus 3b cosine 3x plus y, which we're assuming is a cosine 3x plus b sine 3x, and this is supposed to be equal to 2 sine of 3x. Okay, again, we want to go ahead and distribute, get rid of the parentheses. And let me erase that. I won't really need that anymore. Everything's already plugged in. So here's what we have. We have negative 9a cosine of 3x minus 9b sine of 3x. Distributing this negative sign through, we get a positive 3a sine of 3x minus 3b cosine 3x plus a cosine 3x plus b sine 3x, and this is equal to 2 sine 3x. On the left-hand side, we have a bunch of 3x sine 3x terms and a bunch of cosine 3x terms. So let's group them together and factor them out so we can see the coefficient. Let me first begin by looking for the cosine of x term. So where's my cosine of 3x terms? Well, let's see, there's one here, and one here. Those coefficients, if you group those three terms together and factor out the cosine of 3x, what you would have would be negative 9a minus 3b plus a cosine of 3x. And now if I group all of my sine of 3x terms together and factor out their coefficients, we have a negative 9b plus 3a, and then plus b. And this is equal to, I'm going to write this a little bit weird perhaps, but on the right-hand side we have 2 sine 3x. Notice there's no cosine of 3x term, but I'm going to explicitly put it here with a coefficient of 0. Perfectly fair game, we can do this. And it just kind of helps to visualize the next step, which is now we're going to equate the coefficients. So think of this as the equality of two functions, the function on the left-hand side and the function on the right-hand side. If these two functions are equal, then we would like for the cosine's coefficients to be equal, which means that this coefficient here has to match this coefficient here. That is that, and actually I could have even done a little bit more, negative 9a plus a, let's do that, because it'll make it work a little bit easier. That's negative 8a minus 3b cosine of 3x, and we could have combined some here too as well. That is okay, good. Negative 9b plus b would make a negative 8b plus 3a, and then that's the sine of 3x equals 0 cosine 3x plus 2 sine 3x. But as we just said a moment ago, the coefficient of the 3x term on the left-hand side should match the coefficient of the cosine 3x term on the right-hand side, and therefore negative 8a minus 3b is equal to 0. And the coefficient of the sine of 3x term, which is this guy here, should match the coefficient of the one on the right-hand side, meaning that negative 8b plus 3a should be equal to positive 2. And as a linear system, it's good habits to write the coefficient on the left-hand side in order. So I'll put my a terms first, and then my b terms second. I'm just going to flip-flop these two. 3a minus 8b equals to 2. I won't explicitly solve all of these in the lecture videos. This is kind of just like linear algebra or basic intermediate algebra. But let's at least kind of go through and solve this system together. We have two equations in two unknowns, right? Equation 1, equation 2, two unknowns. Unknown variable A, unknown variable B. We can solve this one in particular using the elimination method. What I'm going to do is I need to get equal but opposite coefficients. So maybe I'll try to eliminate the A variable. So if I want to solve, let's say eliminate for A, if I want to eliminate A, then I want these coefficients to be equal but opposite. So what I can do is, between 8 and 3, their least common multiple would be 24. So I can multiply the first row by 3, everything, and I can also multiply the next row by 8. That will give us the following linear system, equivalent linear system. So we get the following. This is going to be negative 24a minus 9b equals 0. On the bottom equation, if I multiply everything by 8, we would get 24a minus 8 times 8, 64b equals 0. And now what we can do is add the two equations together. If I add the left-hand sides together, these a's cancel. Negative 9b minus 64b would give us negative 73b. I made a huge mistake here. What is 2 times 18? Well, 2 times 18, that should be 16. So that when I add the two together, zero plus 16 will give us 16. And we've now effectively eliminated the a variable. We can solve for b by simply dividing both sides by negative 73. And we get everybody's favorite fraction, I'm sure, b equals negative 16/73. So that's good. At least now we know what b is. We can go back and solve for a by plugging b. It's oftentimes easier to plug it into one of the originals. Doesn't matter. I'll plug maybe it into this one right here. So let's go ahead and solve for b. We know that 3a minus 8b equals to 2. Everywhere I see a b, I can replace it with negative 16/73 equals to 2. This would be 3a, a negative times a negative will become a positive. 18 times 16/73 that is going to be 128/73 equals to 2. We're now going to subtract 128/73 from both sides. Again, don't be put off. This is just arithmetic. It has nothing to do with the differential equation. We get 3a equals. Again, get common denominators, all that good stuff. It's okay to use a calculator too. But we would get 18/73. And then you can divide by 3. I find it perhaps maybe a little bit easier to multiply by 1/3. This is some arithmetic I can do in my head. Cancel this. 3 goes into 18 6 times. And so we get that a is equal to 6/73. And now we have found our particular solution. So y sub p, remember going back to when we defined it, it was of the form a cosine 3x plus b sine 3x. A is 6/73 and b is negative 16/73. Therefore, our particular solution is going to be 6/73 cosine of 3x minus 16/73 this sine of 3x. And so that gives us our particular solution. The last thing we're going to do is we're going to put it all together, and we're going to write out the general solution to our differential equation. So again, as we said a moment ago, the general solution is simply found y is nothing more than the complementary solution plus the particular solution. So it's going to be y equals, we wrote that down earlier, it was e to the 1/2 x times the cosine of the square root of 3 over 2x. And I'm forgetting a c1 here. Let me squeeze that in. I knew I would. X times c1 cosine of radical 3 over 2x plus c2, the sine of the square root of 3 over 2x. That's y complementary plus y particular, which we know is now 6 over 73, the cosine of 3x minus 16 over 73, the sine of 3x. And so there's our general solution to the differential equation. We solve the homogeneous solution, the homogeneous linear ODE to get YC. We look at the form of g of x when we solve the non-homogeneous differential equation. We look at its form. Based upon the form, it gives us a suggestion for what the particular solution would look like. We take the particular solution after finding derivatives, plug it into the differential equation, and then we solve for those undetermined coefficients a and b. And then at the end of the day, our general solution is simply the complementary solution plus the particular solution, which is this.